All right, so next thing we're going to deal with is the last way to find delta H. Up to this point, we reviewed the other two in the first video. We reviewed Hess's law, which is where you flip the reactions, Price is Right style. Second one was heat of formation, products minus reactants. Third way of finding delta H is bonds broken. It's a little different. Bonds broken minus bonds formed. You'll need the bond energies, which will usually be given you in a table. So if you look, here's a bond energy table from our textbook. And basically, you have to remember that you do this. Key part is first you'd have to draw the Lewis structures because you need to be able to see the number of bonds and the kind of bonds. So that's the first step. Draw the Lewis structures. Step two, you get the bond energies from the table, use the number of bonds from the Lewis structure and your stoichiometric coefficient to find the value for each of them. Then what you do is you take all those values, you total the bonds broken, then minus bonds formed, and you get delta H. So the key thing is finding the number of bonds, or actually the bond energy. This is supposed to be bond energy, stoichiometric coefficient, number of bonds from the Lewis structure, and I'll show you that in action. So if we look right here, NH2, or N2. So if we draw N2, we get this. N triple bond, technically you should be able to draw this. H2, I draw the Lewis structure for that. And if I draw the Lewis structure for this, you end up getting N, this, H, well, it's kind of drawn, kind of jacked up, but you get the idea. Like that. So you draw the Lewis structure. You probably have, actually, let me fix this. Be like this. Maybe not like that. So there's the structure. So first thing I do, I take the value from the bond energy table, which is going to be N2 triple bond is 946. So I come back here and I go 946 times the number of bonds. I only have one triple bond, so it's 1. Stoichiometric coefficient from the equation is 1. So 946 times 1 times 1 is going to be 946. Next one, HH bond. If I go back to the table, my value for an HH single bond is 436. So then I'm going to do the exact same thing. I'm going to take 436 times the number of bonds I see on the Lewis structure is 1. Coefficient of the equation for that is 2. So then I'm going to multiply all those together. So then what I'm going to do is I get 872 for that. Whoa. I get 872 for that. And what I do is I'm going to add the two together to get my bonds broken. So 946 plus 872 is going to be 1818. So for my bonds broken, come back over here, I have 1818. Now I have to do bonds formed. So I go back over, I look at my Lewis structure. First bond I'm going to do is going to be the nitrogen to nitrogen single bond. So I have a nitrogen to nitrogen single bond. So if I go back over here, nitrogen to nitrogen single bond is 163. I see it right there. So I'm going to go back. I'm going to take 163 times the number. I have one of them. Coefficient from the equation is actually 1. It's hard to see. That's going to be equal to 163. Next one, nitrogen to hydrogen single bond. So I go back here. Nitrogen to hydrogen single bond is 389. So I'm going to go back over here. 389. How many bonds do I see in that molecule? 1, 2, 3, 4. Number of bonds. Coefficient in the equation is 1. So then what I'm going to do is I'm going to take 389 times 4, and I end up with 1556. I add that together plus the 163. That's going to give me 1719. So then I'm going to go back over here. Minus 1719. I subtract the two values, so 18 minus 1719 is going to be 99. So it's going to be 99 kilojoules would be my value for delta H for the reaction. That's the last way we do delta H. Okay, so we did that. Last step in thermodynamics has to do with delta G. Delta G, we figure out delta G two different ways. We can do it by inspection, requires a little memorization, a little critical thinking, or we can do it by calculation. Key thing you need to remember is When delta G sign is negative, it is spontaneous. When it is 0, it is at equilibrium. When it is positive, it is non-spontaneous. So we go to look at delta G. First thing is the table. How to determine? Well, you can determine based on the signs. So you have delta S values and delta H values. Based on the signs, you can infer whether or not something is spontaneous and at what conditions it would be. So if we start out with always spontaneous is going to be when delta S is positive and delta H is negative. That is always. Okay? Never spontaneous is the exact opposite. So if I take delta S is negative, delta H is positive, that is never spontaneous. Then you get into two situations where temperature matters. If you have S positive and H positive, so I have a positive delta S, positive delta H. Think of a thermometer, plus, plus. High temperatures on a thermometer, when there's a lot of pluses, means it will be spontaneous at high temperatures. So the other situation is when delta S is negative and delta H is negative. Well, if delta S is negative and delta H is negative, then it is spontaneous at low temperatures. Think on a thermometer when there's a minus degree temperature, it's very low. Think of it like that. It's an easy way to remember it. So the only time you really can draw an inference when something is spontaneous at certain temperatures when the signs are the same. So positive, positive, high temperatures, negative, negative, low temperatures. So look right here. They want to know which cases. This is by an inference. So first thing is my delta H value is negative. They gave that to me. So I have a negative delta H value. I need the delta S value. Well, if I notice gas, gas, and gas, so then it goes by the mole rule. I have 3 moles on this side, 1 on this side. My delta S value is going to be negative. H is negative, S is negative. If we go back and look at the chart, when H and S are negative, we say it is spontaneous at low temperatures. So we would say this would be spontaneous at low temps. Next one. If you look, gas, 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 delta H value is positive. It goes from a value of 1 on the left side to 2 on the other side. Delta S value, therefore, would be positive. H is positive, S is positive. This reaction will be spontaneous at high temps. Okay? Again, when the signs are the same. Look here. Delta H is negative. What's my delta S? Well, first thing I look at is gas, gas, gas. I can't use the SLG rule. I have 2 moles on the left, 1 mole on the right. Means my delta S value is negative. That is going to be spontaneous at low temperatures. Next one. Gas, gas, gas. Delta H is positive. Delta S is also going to be positive because I have 2 moles here, 4 moles there. Therefore, it's going to be spontaneous at high temperatures. Look at C, gas, whoops. Gas, gas, gas. I have 2 moles on the left-hand side, 3 moles on the right-hand side. Therefore, my delta S value is going to be positive. Delta H value is going to be negative. This would be always spontaneous, meets the conditions. One way we calculate out delta G, the one that's used the most often, and on some of your sample problems on your free response, they're asking you whether or not it's spontaneous. What they're really asking you to do is use going home to supper. So going home to supper is the calculation for Gibbs free energy. Once we find the sign for delta G, we can figure out whether or not something's spontaneous or not. So notice you have delta H here, delta S here, and you have T for temperature. So at a given temperature, you can calculate whether or not something's spontaneous or not. So if you look right here, calculate the delta G. I'm given H values. Notice the elemental values are 0. I'm given S values. Everything has an S value. If you notice, the units for H and S are different, kilojoules and joules, and we'll have to make an adjustment. So when we go to do this, products minus reactants, you should end up with a negative 92.22 kilojoules for delta H. Delta S, we end up with a negative 198 joules per degree Kelvin. We have to adjust S when we use going home to supper. So when we go over here, we're going to take the negative 92.22, temperature 25 degrees Celsius is changed to Kelvin, and then we take the S and we modify it to kilojoules. So we bump the decimal over 3 places, then we do our calculation, so delta G always comes out in kilojoules. So negative 32.91 kilojoules. We would say that this reaction, we could be sure that the reaction occurs spontaneously at 25 degrees Celsius because the sign for delta G is negative. All right, another way to calculate delta G is you could do products minus reactants. You do that, get the values from a table, plug those in. Very rare on the AP Chem exam, but it's possible. Very easy, just take the values from the table, products minus reactants like we've done before. Now, one of the things they always ask you to do on the free response question, if it's thermodynamics, is solve for KEQ, or equilibrium. Here's the setup that's in your AP handbook. I ask you to do it in the free response question. Remember, R is 8.31 joules. So that's R. T is whatever temperature they decide to give you, has to be in Kelvin, and then the natural log of K. When you go to plug this in, remember to change delta G back to joules because the unit of R is in joules. So what you have to do is change whatever value they give for your delta G. You have to blow it up, add 3 zeros to the end of it to make sure the calculation is very simple. So then you basically cross multiply the R and the T. So it's delta G over negative RT is going to be equal to the natural log of K. And then once you solve, basically you do a little algebra. E to remove natural log, remember E the other side, so delta G over negative RT. Another relationship you have to be aware of is that when delta G is 0, KEQ is 1. So if you're using going home to supper, and they ask you this fairly frequently, they ask you when it's going to be at equilibrium, at what temperature. All you're really doing when you do this is take going home to supper, and they say, hey, what's the delta G value at equilibrium? Or when does it go from being spontaneous to non-spontaneous? In all those conditions, all you're doing is setting delta G equal to 0. And then basically plugging in the delta H, plugging in the delta S, and then solving for delta T, or not delta T, but solving for temperature. So whenever they ask you to solve for it at equilibrium, know that when it is at equilibrium, K is equal to 1, delta G is equal to 0. Other instances, if K is larger than 1, we know the reaction is spontaneous, which means delta G is going to be negative. If K is less than 1, we know that delta G is going to be positive because the reaction will be non-spontaneous. Those are things you would need to memorize and just be aware of. So if you look right here, this kind of sums up thermodynamics. The whole point of thermodynamics is to solve for delta G. We have 3 ways of finding delta H. We can do it by bonds. We just did that at the beginning of the video. You can do it using Hess's law. You can use a heat of formation table. When you see the sample problems that I give you, they'll have little pieces of each of the ways to solve for delta H. You plug it in, it's kilojoules, it goes in right there. Delta S is only one way to calculate delta S, products minus reactants. Gets plugged in there. And going home to supper, be sure to convert to kilojoules. That's what you have to remember to make sure that you convert delta S into kilojoules, and then T must be in Kelvin. And remember the equilibrium calculation, I just showed you that before. To solve for equilibrium or KEQ, you would be given a delta G value, you calculate it, you go through and do your calculations. And that brings us to the end of thermodynamics. Take a look at your Chuck Norris 3 Spring Break Special, which will go through and tell you, give you practice on each one of these calculations. It's important to make sure that you practice. Have a good rest of your spring break, and I will see you on Tuesday when we get back.